Hello, my name is James Hool. I'm the director of the UNH Stormwater Center, and I'm going to cover BMP accounting and tracking real-world applications. The UNH Stormwater Center has been working with the BMP tracking and accounting tool for a while now, and much of our data has been used to calibrate the local applications in the region, throughout the region. In the previous videos, you've learned about the history of the BATT and its application from a regulatory context, and secondly, how to enter data and really the mechanics behind reporting. I'm going to take you through a real-world example and the nuts and bolts of how the accounting architecture is stitched together. The four main topics that are really important to this discussion is what makes a good tracking and accounting system. What elements of stormwater control measures, both structural and non-structural, does the BATT track? What is important to track? And what does this look like in practice? Tracking and accounting systems identify common denominators to interact with crediting and reporting systems. It follows hopefully a consistent regional approach and provides certainty to both permittees and permitters. Consistency here is the name of the game. It's reproducible across the watershed, and it demonstrates progress, at least on paper, while we wait for the scientific data at the receiving water to record the results of the implementation measures. When you actually get into the model space of the BATT, it tracks hundreds of design details. Some of them are really important to various interest groups, but in order to get going, you don't need all of them. There's lots of important things that can be tracked, but if you're looking for the minimum number to track to identify and quantify water quality improvements, we largely focus on four primary elements. The holy grail of what you need to account for water quality improvements are really four things. The BMP type, those are largely defined already in the MS4 for New Hampshire and Massachusetts. You need the impervious cover area, and we focus on impervious cover because in the range of storms that we're designing for, it's really only impervious cover that's delivering the relevant aspect of excess precipitation runoff. 3, we look at the infiltration rate, and that's according to the hydraulic soil group in inches per hour. And we look at what is referred to, at least in the permit, as the design storage volume. The design storage volume is the physical capacity of the actual BMP to store water, and the physical storage capacity is related to the drainage area in inches of precipitation depth. So the volume of water the system is able to store in relation to the drainage area that's delivering water to it. It will be sized for a certain rainfall depth, and that is typically in the model spaces between 0.1 inches and 2 inches. So next we're going to talk about what this looks like in practice, and I'm going to introduce a relatively new adaptive management framework that was ushered in very recently in southern New Hampshire with the Great Bay Total Nitrogen General Permit. EPA Region 1 recently issued the Great Bay Total Nitrogen General Permit to 13 eligible communities in southern New Hampshire. It includes an adaptive management option. The general permit establishes nitrogen effluent limitations at the wastewater treatment plant, but also provides the option to account for load reductions associated with structural and non-structural stormwater control measures. So by structural, I mean the 10 or so modeled structural controls from bioretention all the way down to impervious cover disconnection. And then for non-structural, for the most part, it is leaf collection activities, street sweeping, and catch basin cleaning. There are many others that can be accounted for, but the process of developing actual credits is a little bit separate from the process of tracking and accounting for them. In addition to quantifying control measures that have been implemented and the attendant load reductions associated with them in the recent past, with these same metrics, we can develop consistent plans for the future. Since we have consistent methods across the watershed, we can use them to prioritize municipally owned land. And again, these are consistent with all of the loads and associated pollutants that have been throughout the region. So we're using the same underlying metrics. In this instance, what we've done is we've looked at municipally owned land, and we've developed a performance curve associated with the cumulative percent of total impervious cover management that a community might have to do to target the optimal range of impervious cover. So when we look at across, say, the city of Dover, and we look at their 80 or so municipally owned properties, we identify 22 parcels that, if retrofitted, represents 89% of the impervious cover that the municipality actually owns. We can turn that into a prioritized list, which you see here on the right, which is basically the foundation of what we'd call a nitrogen source identification report. This prioritizes municipally owned lands by their size and impervious cover. So here we're going from 14 acres all the way down to a little bit less than 0.8. So these 22 properties represent 89% of the impervious cover that the municipality owns. And that's what you use this knee of the curve tangential estimate to identify an optimal implementation target. Another thing we can do with standard and consistent tracking and accounting is we can develop programs that interface with the BATT accounting system. PTAP, or the Pollutant Tracking and Accounting Project, which has been developed to meet the needs of permit holders in southern New Hampshire in the Great Bay region, is an authenticated tracking database that integrates with the BATT and its accounting. So we actually provide this authentic user interface so that communities and developers that are developing in communities can enter this important information into our tracking database. That would be associated with any development that's happening, or it could be associated with municipally driven implementation projects. And this is one example of a large, what we call a regional stormwater facility. So a facility that is taking a large amount of drainage from existing impervious cover and directing it to a local area where it's treated. And we can use the BATT in order to account for the actual load reduction. Since PTAP uses the same math, we can integrate between these two resource tools. So whether you're using a formal tool like PTAP, or whether you're tracking this information on your own in something as simple as a spreadsheet, the math is consistent, and that then gives us access to the full accounting capabilities of the regionally derived tools. So in this case, I'm showing you a front page from the PTAP user interface, and you notice that we're looking for those 4 fundamental things that can translate the system effectiveness across these 2 tools. We're looking for the BMP type, and we have drop-down menus for the 10 BMP types. We're looking for the impervious cover, and we're focused on impervious cover, and we're looking for infiltration rate, and there's a calculation for design storage volume. And you can look into, we have tools online that go over how design storage volume is actually calculated, and associated with that, how physical storage capacity is calculated, or you can look at these in some of the information in the user guidance for the BATT. So video 2 covers how to enter data into and use the BATT as a direct entry method, but the BATT also has a couple of other unique features that I wanted to point out. And these are this import-export function, which you see in the left-hand picture right in the middle, that middle green button. And this is a very powerful tool because this is what we take advantage of. Again, we align the data consistent with the BATT, and we're able to export a CSV file from our database and then import it directly into the BATT database. From there, once our project is imported, we can develop a project summary report, again with these same consistent values, such that we're confident that the information has been calculated to the extent that the science allows. Another important component is as the science changes, and it will change, since we're regionally developing these standards in the same consistent way, we can update them without having to go back and collect additional information about the stormwater control measures that have been implemented. So what I'm showing you in this slide is the basic report out summary field from the BATT. So we've used the import feature to import our project. In this case, it's a development in an example development in a permitted community. And then from all the information that's been imported into the BATT, we get these fields that show us the phosphorus load removed, the nitrogen load removed, and the sediment. We focus on these three things, although we can calculate others because they're primarily what is driving permit requirements in the region. So it's either phosphorus inland or it's nitrogen in coastal areas. The table below also provides the individual systems and what their removal efficiencies are. And this is important potentially for say permit compliance. If you've recently updated your regulations and you require a certain say phosphorus removal efficiency, you can use these report functions in order to build defensibility that the site development has met the obligations of your permit. And that is just what some communities have been doing, and this is kind of the exciting layer on top of using a consistent framework. The city of Portsmouth has actually included the use of these database and tracking and accounting tools into their site plan review regulations. So they've inserted very simple language that directing developers as a process of getting a permit to enter information into the database. So if you're going to do this, you make development work for you. And there's, at least in our database, we have individual report features that you can develop for each entry. So if you're only looking at a certain site, not looking across the town or the watershed, you can develop one of these reports and demonstrate that you've met the 90% sediment load reduction and the 60% phosphorus reduction and the 50% nitrogen reduction. That is a good tool. If developers can do that for you, it's possible that that will help the permitting process, as opposed to looking very intensely at each development across the range of things that you're having to look at. And that concludes this presentation module. I hope this has given you some ideas or provided a better context in the way that this can be used and will be increasingly used as we move forward. And finally, again, at least in the Great Bay, what the model tool development has allowed us to do is add accountability in the permitting process, add consistency across the region, and it buys us time such that all the important and meaningful implementation measures that have been done, both at the wastewater treatment facilities and on the non-point source side, it's going to take a while for the environmental data to actually reflect what's being done today. We can't guess. It hasn't happened overnight, and it's not going to return overnight. But this type of accountability buys us the time that's necessary to do the intensive monitoring that needs to be done to show that our receiving waters eventually are meeting their designated uses. Thank you.